You guys hear me?
I can hear you.
Okay. Okay, so today we will continue with quadratic surfaces. So first, going back to what hyperbola or hyperbolas look. 1 second. Okay. So okay, so if we have our x and our y coordinate, so here's x, and here's y. Then we first can imagine these two lines, and the hyperbola will look something like this. And again, this comes about when, let's say you have something like y squared is equal to the square root of x squared plus or minus some constancy. Now, if we got rid of this c, we would just have, y. We would just have y is equal to x, and those would be these lines over here. I mean, together with the fact that it was squared before. So we first should imagine that you have the y squared is equal to x squared plus minus c. So when you don't have the c, you have these lines over here. This is for the when just x is equal to y, and this is for when x is equal to negative, or y can be equal to negative x. Okay. So they ask us, without referring back to the formulas, use the traces to determine and graph the quadratic surface given by x squared plus 2z squared minus y squared is equal to 0. So let's do that. So they tell us x squared plus 2y squared, 2z squared is equal to y squared. Okay. So now we can first imagine that our z is 0. So let's first put a x, y, z coordinate system. Now when z is equal to 0, we have x squared is equal to y squared. So we get two lines. So those would be the lines. So here's your y and here's your x. So it would be like this. And then another line like this. So that would be lines. Now let's imagine that my x is 0. So then we have 2z squared is equal to y squared. So again, we're going to get lines just with a different slope. but this is in the YZ plane. So one of these lines is going to look like this. And another one of the lines is going to look like, second. Oh, we can, there you go. Okay. And then when we have that the y gets different values, so at x squared plus 2z squared is equal to y naught squared, so at different constants for y, we get circles or ellipses with the radius or a radius relating to that. So you would have these circles like this. Each one of them corresponding to a different y naught. And we end up getting a cone. So that's this cone over here. Any questions about this? Okay. Now, another couple of shapes that are useful to remember, the cylinder. So we don't have a Z. The Z is not restricted over here. So that's why you have circles in the XY plane that extend plus or minus infinity. The elliptical cylinder, same thing, just now we're dealing with an ellipse. So you start with an ellipse and you stretch it to plus and minus infinity. The hyperbolic cylinder, you have hyperbolas that you stretch to plus and minus infinity. And the parabolic cylinder, again, you have parabolas that you stretch to plus or minus infinity. So in summary, the shapes that we have looked at, you have your ellipsoid, your hyperboloid, F1 sheet because it has a +1 over here, so everything in the middle gets filled in. And then a hyperboloid of 2 sheets, you have a -1 over here, so there's certain values that here you have positive values, here you have negative values, so they just don't get filled in. The paraboloid, it's made out of 2 parabolas and then circles, so that's why it's an elliptic. And the hyperbolic paraboloid, again, you have 2 parabolas over here, just this time one of them is going up, so that's this red one, and one of them is always going down, and that is this green one. And then you also have hyperbolas over here, which are these. And then you have the cone. The cone is actually also has hyperbolas in it, but it starts off already with the lines that we mentioned. So that's why you get a point versus in the hyperboloid, you don't. Then you have the elliptical cylinder, the hyperbolic, and the parabolic cylinder. Okay, any questions about any of this?
Professor,
Mm-hmm.
last week I asked about general differences between parabola and hyperbola. Can you go over that?
Yeah, so I just talked a little bit over here about what hyperbolas look like. Obviously, they look different than parabolas in that. So this is how hyperbolas look, and parabolas. Well, you would have something like this, and let's say this would be y is equal to x squared. And you don't have any of these lines. You don't have this asymptotic behavior towards the lines. So yeah, they're fairly different. And okay. Okay, so now we are going to continue with vector valued functions. So let me try to find that. And yeah, I'm going to post these videos again on YouTube, and I'm going to add some links to new videos that Joe is making, so you can also take a look at that, if that helps. Okay, good. Vector valued functions. So we're going to continue here. So they first start off by just talking about different RFTs. So here's my RFT, and they say I want my RFT to have an x coordinate. And we already did this with lines. We had very simple RFTs. But now they want to be able to make any curve. So RFT is equal to x of t, y of t, and z of t. Okay. And this is a curve in 3 dimensions. So maybe it looks something like this. And for every point in the curve, if you look at that point, you're going to get r of that t at that point. So this might be t is equal to 0, and so on. And like I said, we already had this RFT for lines. So for lines, we had that RFT is pretty simple. It's just equal to R of 0 plus TV. Okay, so yeah, you have R of t is equal to x of t, y of t, z of t, which is x in the ith component, y in the jth component, and z in the kth component. And and we have these vectors that move along the curve. So you have t1, t2, t3, and you're moving along. You can think about it as a path that a particle will take. So what are types of functions that we can look at? So we can look at r of t is equal to t squared, e to the t 4 minus 7t. So that's fine. That would be a curve. This would be another curve with the following domains. And as I just mentioned, we already had r of t as a line. So this is your x0 plus tv. And this is parameterized the line through this point with the direction v, like we saw. Okay. So now they are giving us an example. They want to find the path versus the curve. So they wanted to describe this as a path versus describing it as a curve. So the z coordinate over here is always 1. So that's cosine, sine, and 1. Okay, so you have r of t is equal to sine. Oh, no, cosine first. 1 second. Yeah, cosine of t. Okay, sine of t. And 1. So whatever this curve is doing in the z direction, it doesn't really change with t. So it's always going to be 1 in the z direction. Here's my x, and here's my y. It's always going to be somewhere here. Now, in general, we can say that, yeah, so you're going to have the height of 1. Now, generally, if cosine is going to be represented by x, and sine is going to be represented by y. So you could say that x is equal to cosine of t. And it is over here, at least, and y, and this is actually x of t. Y of t can be equal to sine of t, which it is. And because of this, well, we get that x squared, so let's go x of t squared plus y of t squared. Well, this is equal to cosine of t plus cosine of t squared plus sine of t squared. So this is equal to cosine squared of t plus sine squared of t. And this is equal to 1. So you see we have x squared plus y squared is equal to 1, so it's a circle. So we're going to end up getting a circle, which is a unit circle. So over here, this is going to be x is equal to 1. And this over here is going to be y is equal to 1. Any questions about this? That's what this picture shows you, a circle. Okay. Oh, and then they ask, how are the path and the curve very different? So the curve would just be a circle, but the path, you would just go, you would keep having to go around it. So as t goes to plus or minus infinity, you would go around the circle an infinite many of times. So they are different objects. And it's good to remember that. Okay. Fine. So now the next one is describe the curve traced by r of t is equal to negative sine of t cosine of t and t in terms of its projections onto the coordinate plane. So they want you to figure this out, but they're telling you, oh, a good way to figure this out is by looking at the projections. So here's my x plane, y, and z. And in my xy plane, so here's my xy plane. So now I can imagine that the z component is 0. And so then I have negative sine of t and cosine of t. And doing the same thing that we did before, so we have, now we have that x of t is equal to negative sine of t, and y of t is equal to cosine of t. So again, x squared plus y squared is going to be equal to 1. So we're dealing with a unit circle. The difference is that we have like a negative sine of t, so that makes it go counterclockwise. So here's our circle. Now, in the xz plane, so here's my xz plane. So now my y is 0. I just have sine of t and I have t. So then we have the sine function. As we move along z, so as we move along z, we get this negative sine of t in the x coordinate. So that would look something like, so generally we would be coming up over here. So now we're going to be going like that. Something like this. And the same exact thing also, we get the same thing just now with cosine of t and t, and now in the y direction. So let's draw another picture here. So here's x, y, z. So in the z, y direction, as you move along z in the y direction, you also get a curve, and this time it's cosine. So it would look something like 1 second. So, yeah, it's a little tricky to draw exactly how it would look because you need to do that. But again, you have a circle over here, and you have in one projection you have your sine, and the other projection you have your cosine, and all together. And this one is actually there. It is easier to see how this ends up giving you that spiral. Without it's actually better to not think about the different projections, I think, in my opinion. So again, if you have your x, your y, and your z, so they tell you that in the end we get a spiral. It looks something like this. All right. And the question is, what is a good way to see this? And the answer is, if you have r of t is equal to negative sine of t, cosine of t, and t. Uh, okay, then this t just makes you go up and down. So as t gets bigger, you're just going higher. As t gets smaller, you're going lower. So that's what this t does. And like I said, this gives you a circle. Because you're going to have x squared plus y squared is equal to 1. So you're going to get a circle, but that goes up and goes down as we vary t. So that's exactly what this is. It's a circle, but it's increasing, but it ends up coming back to the same place where it started from. So it is a circle, but it is also increasing as t increases. And that's why we're going up. Any questions about this? Okay. Okay, so now they want us to parameterize the curve obtained as part of the intersection of this surface over here, and the cylinder x squared plus y squared is equal to 4, where y is bigger or equal to 0. So if you have this over here, and we have this over here, we can say that y squared is equal to 4 minus x squared. And this just tells us that y is equal to the square root of this. So now we can plug this into our surface, and well, we already have a y squared in this surface. That's what they do over here. So now we have that z is equal to, and when we plug that into y squared, we get x squared minus 4 minus x squared. This is from my y squared plus 1. That's from here. And this is going to be equal to 2x squared minus 3. So that is what our z is going to be. Okay. So now if we want to parameterize this, so we already know what our y, what our z, this is our z, and what our x are in terms of x, right? So our y in terms of x is this over here. This is our y in terms of, so all we really need to do is to say, okay, let's take the t is equal to x. So now we just parameterized everything. So now my r of t is going to be equal to t for my x, that's in my t component. It's going to be equal to the square root of 1 minus t squared. That's for my y. And then for my z, it's going to be 2t squared minus 3. So again, when we have a problem like this and we have two surfaces and we're trying to find their intersection, generally you want to have one of the variables be your parameter. You want to turn that into your parameter. So we are choosing x over here. Then your second variable, you want to find what it is in terms of the first variable, and we did that. And then you can use that with, hopefully with the second equation, to figure out what your third variable looks like in terms of your first variable. And that's what we did over here. And we get that z is equal to this. So this is what z is in terms of the first variable. Then you substitute with your first variable, you just take t to reparameterize. It doesn't actually make that much sense. That's such a difference, sorry. And then you can create an equation. R of t is equal to your x, so your t, your y, which again had y in terms of x, so that goes there, and your z. And that again had z in terms of x. Any questions about this? Okay. So now they want us to parameterize the circle of radius 3 with its center over there, located in the plane, parallel to the xy plane and parallel to the xz plane. Okay, so it's always, when you have a circle, and you know its center, here's your center, so you should always try to think about a curve that starts at the center. So it should at least have one vector at the center, sorry, at the center plus 3. So at the center, and then you add 3 to it of that vector. And then you go over here and we can just make a circle. And that's really what they did. So they just say, okay, R1 of t, my circle, is going to be equal to my center. Okay, so that already puts you, fine, here. That puts you here at your center. That's going to be the center. So this is going to be the point 2, 6, 8. Okay, and then you add to that your circle, and the radius of your circle is 3. So before, when we were looking at this and we said, okay, this squared plus this squared is equal to 1, what we can also do, we can have R of t is equal. And now if I, let's say, put here 3 cosine of t, 3 sine of t, and t. So now I'm going to have a circle of radius 3, because now this squared, so 3 cosine of t squared plus 3 sine of t squared, this is equal to 9 times 1. And now, so this is equal to 9, which tells us that the circle has radius 3. So then you would have the same exact circle, just now with radius 3. So in our example, when you look at the center, you add to it a circle of radius 3. So that would be 3 cosine of t, exactly what we just did, and 3 sine of t. And 0, because you want this to be a circle that is parallel to the xy plane. So you don't want anything happening in the z component. You start at the center and then you go around it and you make a circle. That's that circle over there. And then for the second part, if you want it to be parallel to the xz plane, then all you really have to do is you have to put this 0 over here. So that would be R2 of t is equal to 2, 6, 8 plus 3 cosine of t 0 and then 3 sine of t. Okay. So again, this was all about RFTs trying to create different curves in space, in three-dimensional space, and how those curves would end up looking. So let me see. 1 second.
Professor,
Yep.
does it matter if we put 3 sine t first and then 3 cosine t?
No, it just might matter in terms of the direction in which you're going, especially if you, like, put a negative, but it doesn't. It always will give you a circle. It just the direction might be different. Yeah.
Okay, thank you.
Okay, 1 second. I'm just looking for. 1 second. Okay, so I guess we should stop here because we got up to calculus of vector functions, and okay, let me start quickly, and we're gonna, but we're gonna stop early, I think. Let me just explain what we're gonna end up doing next week, and then we can continue this next week. So we basically want to now take a lot of the things that we had from Calc 1 and Calc 2 and just import them to Calc 3. So if you have, for example, your R of t, we can talk about the limits. The same way we were talking about limits before, we can talk about the limit as t goes to t not f R of t. And it's actually fairly simple what you end up doing. You just put the limit in each component. So the limit as t goes to t0 of R of t is going to be in each component the limit, and each one of these is now a single variable. Well, yeah, single variable, in our case only t, so we can deal with it in terms of its single variable, x of t, and the limit as t goes to t0 of y of t, and the limit t goes to t0 of z of t. And so for example, if you want to find the limit as t goes to to 3 of R of t, where R of t is equal to this, so you, in each one of these is actually continuous. So you can just place the t in each one of them. So they put it in each component, and then they just put it inside. So t squared is going to be 3 squared, which is 9. 1 minus t is going to be -2. And t to the inverse is 1 over 3. So they just plugged it in. And then we can create a derivative. Because we have limits, we can now look at the derivatives. And just like before, the derivative r prime of t is going to be the limit as h goes to 0 of r of t plus h, r minus r of t over h. So this is Same exact definition as the derivative that we had before. And we actually get that the derivative is the derivative of each component. That's just what the derivative will be. You take each component in terms of t, and you're going to get the derivative function. So the derivative of this t squared, t to the third sine of t, well, t squared, its derivative is 2t. T to the third is 3t squared, and sine of t is cosine. So that's how we get that derivative. And from this over here, the derivative of cosine is negative sine. The derivative of the derivative of 1 is 0, and the derivative of e to the 2t is 2e to the 2t. So we're just doing each component individually. And yeah, you can take one derivative, two derivatives, and so forth. Okay, so we're going to continue doing this more rigorously next time. Just wanted to express what we're going to continue doing next week. In general, we're going to see that one of the next stages is to take a lot of the ideas that we had in Calc 1 and Calc 2 and to apply them to the different things that we just constructed in Calc 3. Okay, are there any questions about this? Oh yeah, then have a nice week.
Professor,
Yeah.
I know I asked this all over again, but I think because I came late, so I didn't catch about the difference between hyperbola and parabola, and I just like so confused about it.
Okay, yeah, so let me just mention it again. One second. Sorry. Okay. So okay, so the parabolas are just in the form of y y is equal to x squared, let's say, plus, I don't know, let's say c. So anything in this form is going to, so the plus c is going to tell you where you intercept the y-axis, and then you're going to have a parabola. And if you go to plus and minus infinity in terms of your x, you're going to go to plus and minus infinity in terms of y. So these go to infinity. They don't have any asymptote. Like there isn't a line that I can draw saying, oh, here's a line. Well, okay, they might not cross this specific line, but they're not asymptotically approaching this line. So they don't have any asymptotic behavior towards any line. And in this equation, I just get one parabola just pointing up. If I put a minus over here, then it flips, and I get this. Okay, and if I exchange the y and the x, I would get parabolas that look like that. Okay, but again, they're all parabolas. The hyperbola, well, we started with an equation that had something like, we honestly, we just end up with an equation y is equal to square root of x squared plus or minus c. Okay, so in order to understand how these shapes look, you can first imagine erasing C over here. So now you're going to have, if you erase C, you're going to have y is equal to the to x squared, and then you take the square root. So that's definitely going to give you this line, y is equal to x. And because that we can look at the negative x and square it and then take its square root, we would also get this line. So that's if you don't have a C. You have these two lines, and that actually is what makes you gives you the cone. But now if you take away, if you add the C over here, you end up getting hyperbolas that approach this curve asymptotically. And you end up getting 2. Again, one corresponding to the positive, one corresponding to the negative x. They approach these lines asymptotically. They're characterized around here with like a vertex or whatever. But again, I don't want to go in detail into all that. I just want to express, you know, how this shape looks, and more specifically, what is its relationship with regard to these two lines, and versus this shape, which does not have any asymptotic behavior or anything like that. And again, in order to understand the shape, you can just erase the C, you see the two lines, then you add it, you get your hyperbolas. Does that help?
So the intercept there is C, right? On the red line, the intercept with x-axis will be C.
So now you just have to set your y to be equal to 0. So then you have, yeah, x squared plus that. You move it to the other side, you get the square root. So that's what,
Okay.
yeah, for minus would be.
Okay, gotcha. Thank you so much.
Okay, good. My pleasure. Okay, so if there are there any more questions?
When are you gonna post the for Tuesday lecture?
The videos?
Yeah.
I'm going
Can
to
you
try to
post?
post everything this weekend, as soon as I can.
Okay.
Okay? Fine.